In this video, we're going to talk about straight current carrying conductors. So here we have a current carrying conductor, let's say carrying a current I, and the magnetic field that it produces, as you can see, are circular ones around the wire. And so, first of all, we have to figure out how to deduce this flux pattern. And to do that, we use the right hand grip rule. So simply hold up your thumb and make like a thumbs up kind of sign. Bear in mind, this is the right hand, not the left hand, right? The thumb should always point in the direction of the current. And then your four fingers will wrap around either clockwise or anti-clockwise. And these will represent the direction of the magnetic field, B, magnetic field strength, should I say, around the wire. And so in this case, the fields go in a, well, you can call it an anti-clockwise way around the wire. One way that these are commonly represented in the exam, okay, your wire's current could be going into the page, typically represented by a cross, or it could be going out of the page, typically represented by a dot. So if you use your right hand grip rule for this example over here, simply point your thumb into the screen and your fingers will all go clockwise. And so your magnetic field can be drawn as a series of concentric circles, but the gap between these circles, of course, have to be getting larger and larger, right, to represent the fact that the magnetic field is getting weaker. Sorry, the magnetic field strength is getting weaker as you move further from the wire. Similarly, if the current is coming out of the page, then your magnetic field lines look a little bit more like that. So you're going anti-clockwise instead. So one thing that is quite new in the A levels is that we need to be able to quantitatively calculate the magnetic field strength, or more commonly called the magnetic flux density. So the magnetic flux density is represented by the letter B, and the formula for the magnetic flux density created by a straight current carrying conductor is mu naught I over 2 pi r. Mu naught is a constant called the permeability of free space. It's equal to this in SI units. And so what you'll see over here, all right, and of course magnetic flux density, remember the SI unit is the Tesla. And what you see over here is quite intuitive. So the magnetic flux density is directly proportional to the current. So if the current is stronger, you get a stronger flux density. But it's also inversely proportional to R, the radial distance from the conductor. And so if this is my conductor here, and I wanted to find the magnetic field strength, let's say over here, then R has to be the radial distance. And so that's the distance that forms a right angle over here with this wire, right? So it cannot be this, nor can it be this, right? It has to be the line from the point to the conductor, and it must be normal to the conductor as such. And so you'll notice that B is inversely proportional to R, which again makes sense, right? So the further away you get from your conductor, the less intense the magnetic flux density becomes.